Okay, good afternoon. So I am Arghya and I will speak about gap statistics of two interacting random tumble particles. And this is work done here with Abhishek and Anupam. So I just explain the terms here. I am interested with only two particles and two random tumble particles, which is a special class of active particles or active systems. And so the active systems is quite ubiquitous in nature, and almost anything, for example, starting from bacteria to birds to human to animals, these are known as active particles. Active means it has some internal mechanism with which it converts the energy taken from environment and it creates some directional motion. So why this is interesting? This is interesting because it gives rise to some exquisite non-equilibrium features. For example, as you see flocking and very interesting patterns, and also when many such agents are together and you can find some phase segregation or phase transition kind of properties. The distribution is non-Boltzmann, which immediately says that this is far from equilibrium. And also in some particular parameter region, it shows giant number of fluctuation and so on. So there are several such properties. We will be mostly interested about this phase separation and clustering. So the point is that, for example, this is an experiment. This is reported in this paper, and also a simulation has been done. So it is known that when many such active agents are there, after some certain densities, you get a phase segregation. The point to notice is that the particles are interacting and the interaction is repulsive. Still, you find clustering. So the natural question is, this is known as motility-induced phase separation. So this happens only for active particles. So their motion and the interaction, their interplay that creates these kind of things. But the theoretical understanding is the question we will be addressing. People have tried several hydrodynamics approach over quite long time, but the hydrodynamics is mostly phenomenological. That means you don't have any first principle derivation from the microscopic dynamics, or you don't really have a statistical mechanics for this kind of systems. So the question of connecting microscopic dynamics with this emergent behavior is still open. And for understanding this, to get some insight, we take the simplest possible approach. For example, here what you need first of all activity, and second you need interaction. So we just confine ourselves with the minimal model in which you can incorporate these things. So the minimal model is two particles. So you have two active particles and they are interacting, and you see what features that emerge, and then you can think of the many particle scenario later. So here I will be working on the random tumble particles, which is a very special kind of so-called scalar active particle. The random tumble particle motion is defined as something, say for example a bacteria or some microscopic agent which is running in a single direction with some constant speed v, but this rectilinear motion, this is interrupted by occasional tumble, and this tumble happens with some rate omega, and this specifies the dynamics of the system. And in addition, you can put external noise onto it, and you can define the model on a lattice or on continuum or whatever setup you like. So here we will take these random tumble particles, two of them, and we will study the gap statistics, because we expect that the gap distribution that will incorporate the effect of the interaction and whatever external parameters or drive it is there. First, we will say that there are some earlier work. This idea is not entirely new. In 2016, this setup has been discussed in this paper. What they have done, they have put these random tumble particles on a lattice and studied the same gap distribution, but there was no external noise. They found some kind of effective attraction on a lattice. However, when you take the continuum limit, because most of the bacteria or whatever experimental system, it moves on continuum, so we are really interested in studying the properties on continuum. In the continuum limit, there is no non-trivial structure. For example, the particles, x is the gap between the two particles. The particles are either independent, so their gap distribution is constant, or they are on top of each other. So really, no interesting scale is emerging. And on the other hand, there have been some proposals in which it is claimed that you actually need finite external noise to see the phase segregation. So we really ask that what are the minimal requirements in a model to find some interesting structure, and whether the introduction of external noise help us in this regard. And if we have some interesting results, then we can extend it to many particle case. So we take this model here, and we just show you the trajectory first. So this is the trajectory of two run and tumble particles who are subject to external noise. It is known that for a single particle, you can actually devise a effective passive description so that their long time behavior is same. But as soon as you introduce two particles who are interacting, then the nature is very different. You can see that these two particles are run and tumble particles, and these two are the effective passive particles. But when they are interacting, when they are close together, they try to stay close together. This is not the case in passive system, even with effective equivalent parameters. And also in presence of diffusion, the particles are not really on top of each other, so we expect that there will be some scales emerging. And actually this is the case. You can actually exactly solve the system in its on a ring, the steady state on a ring, or you can actually calculate the last time behavior on infinite line, and you see that there are this kind of new terms emerging where these exponentials are cut off by these scale factors. These xi1, xi2 are some new scales, and these scales are some simple powers of the noise strength. So as there is external noise, so some scale is emerging, and when the noise is gone, there is no scale in the system, as we have seen earlier. So some spatial structure is there, and we will see that not only spatial, but it also gives us to very interesting temporal structure. Before that, we just show you another interesting thing which may help us to understand MIPS. We hope that if you calculate the steady state distribution, this can be explained in terms of an effective potential between two passive particles. You have active particles, their interaction is repulsive, hardcore repulsive, there is an attraction. But when you calculate the steady state mimics an attractive interaction between two particles. So an attraction is emerging. So it is really tempting to see or to think that this effective attractive interaction, when you impose it on many particles, that may give some explanation for the phase segregation and clustering you have seen. And this is future. In future, we will try this. And regarding the dynamical properties, we have calculated the relaxation rate. So for example, the system is in a steady state, and you just part up the steady state a bit, and you ask what is the time scale in which it is relaxes back. And this relaxation rate, this shows very interesting feature, very interesting properties, interesting dependence on the system parameters like system size or noise strength and so on. So when the system is small, the relaxation rate is constant. But when the system size is very large, then it is 1 by L square. So what is happening is that there are actually two dynamics is involved. One is the tumble dynamics of the particles, so that the particles go and tumble. This gives you one time scale. And another is because of the external noise, there is the noise-based spreading, which is the diffusive time scale, L square by D. And for small systems, this L square by D is small, but this tumble dynamics is large, and this tumble dynamics governs the relaxation. So this is why it is constant. But when the system becomes large, then the tumble dynamics relaxes very fast, but the spatial distribution is not. So there is really an interplay between these two kind of time scales, and this gives rise to this kind of dependence of the relaxation rate. And it is interesting to note that where this system size dependence emerges, this also depends on the noise strength. So the noise strength, this determines the relaxation property also. I mean, gives rise to some interesting features there. And you can actually calculate exactly the distribution near the steady state, I mean the time dependent distribution, and this goes well with our simulation. You can also solve this problem for very small time and very large time on an infinite line. And here we have found that on the infinite line, actually in next slide you will see that this is a diffusive scaling and this is actually Gaussian. So when the two particles are very far and you are looking at the long time limit, so you can imagine that the particles have done so many tumble events that these are effectively a passive particle. So this is why this Gaussian kind of tail this is coming. However, when the particles are close, as you have seen that when they are close, the trajectories are so different, and this signature is carried by this short gap distribution. Actually, this is exponential. As you are decreasing the gap, the distribution is exponentially increasing in this region. And this is a remarkable signature of activity and the interplay of activity and noise. You can actually take the d tends to 0 limit and you will find that this exponentially increasing thing will become a delta peak. So, this is the spatial and temporal characterization of this two particle system. And in summary, we have analytical results which underscores the effect of noise in emergence of the interesting spatial and temporal structures in active systems. We have characterized the steady state distribution and identified a effective two-body attraction. Also, we have seen that the relaxation rate, they have some non-trivial dependence on the system parameters, and even on the infinite line, the particles show very interesting short distance affinity. And at the noise tends to 0 limit, this gives rise to a jam component. And it will be really worthwhile to see how these features translate to the interacting many particle case. That's all.
Thank you, Arghya. Do we have any questions? If not, then let's have another talk by